All right, so I want to talk a little bit about the birthday problem. I had a few questions about it, so I just wanted to clarify before you did it, or even if you've done it already and something wasn't clear, you can go back and fix it. There's still a few more days on that. So, um, a lot of you have been to a casino before, and if you go up to a roulette table, you'll see something that looks like this thing. So, this tells us what has happened on the last 10 spins on the roulette table. And we know that if we looked at the actual numbers and colors that are on a roulette wheel, there's going to be a bunch of black, a bunch of red, and then a few green. So without getting into the probability of those, this is going to give us the empirical probability of the next spin. And so what that means is we could expect that on the 11th spin of the roulette wheel, the probability of it coming up black would be, well, we have 1, 2, 3, 4, 5. So it'll be 5 out of 10 total. Same thing for red. There's 1, 2, 3, 4, 5 red out of 10. And so if the next spin happened to be red, and this thing down here was red, then now we would expect the probability on the next spin being red to be 6 out of 10. And that would mean that the probability of black coming up next would be 4 out of 10. Of course, that's not the actual classical or theoretical probability, but it's the probability empirically given what's happened so far. So if we were to do the same thing on flipping a coin, we know that if we have just a normal coin that is heads and tails, then the probability is going to be 50-50. So the probability of flipping a heads is 0.5. Probability of flipping a tails is 0.5. That's theoretical probability. So let's say that we flipped a coin 5 times, and we got a heads twice, and then we got tails 3 times. That would mean that the empirical probability of the next flip being heads would be 2/5, which we know is just 0.4. And the empirical probability of a tails next is going to be 3/5, which is 0.6. Okay, so I want to look at the birthday applet real quick. So we will need this thing to be set at duplication. So right here, it automatically sets it V, but we want it to be on duplication. And M is it's going to be 365 number of days, and N is going to be equal to whatever their class size is. So in that Google Sheets sheet, however many people put their birthdays on there, if you want to use that, then that's going to be your N value. So let's just say that we had 20 people in our class, so N is equal to 20. And I haven't actually run any experiment yet, but down here, right here, this thing is giving us the theoretical or classical probability of there being no students in the class having the same birthday. That's what the 0 is right here, that row. The 1 row right here is the probability, the theoretical probability, that at least 2 students in the class have the same birthday. Now what that means is when we basically run a random number generator, we're getting any number between 1 and 365. So we can basically make that correspond to a day of the year. So if we were to run this and we end up with none of the same birthdays here, no overlaps, then what just happened was we have our theoretical probability on the DIST. So that's never going to change because unless we change n, meaning we need more students or less students. But over here, this is giving us the probability based off of how many times we've run the experiment. So you can see that we didn't have any overlaps. No two students in this class had the same birthday. And that's why the probability that no two students had the same birthday in this case is 1, based off of just that one trial. And that means that the probability that at least two in the class, at least there's the probability that there's at least one overlap, meaning two students in the class have the same birthday, is 0. Now if I run it again, we got an overlap of 251. So again, the DIST is going to stay the same. That's always giving us our theoretical probability. But now we've had one run so far that gave us no overlap, and then one run that gave us an overlap. So we're saying that our theoretical probability is going to be 0.5 because it happened once out of two trials. All right, so if we do it again, no overlap. So you can see that now our probability for there being no overlap, no two students with the same birthday, is going to be 2 out of 3. The probability that at least two students have the same birthday is going to be 1 out of 3, or 0.33 repeating. Right, so if I run it again, no overlap. We get one overlap here. So now we've run this 5 times. That's giving us all of our trials. And you can see that we had an overlap right here, meaning two students in this class had the same birthday, and then two students in this class had the same birthday. So 2 out of the 5, which is 0.4, that means that 2 out of 5 is going to be our probability that two students in the class have the same birthday. Again, DIST is our theoretical probability. Data is based off of our data, meaning out of the 5 trials that we've run so far, how many of those classes that we've considered actually have an overlap. So what we can do here is, I'm going to restart this. We could set the stop to 100, and if we run that, this is giving us all of our scenarios, all of the different classes that we've looked at. We've looked at 100 of them, and it looks like we got 0.54 as our probability of no two students in the class having the same birthday, and 0.46 as at least two in the class have the same birthday. 0.46. Right, so that's after 100 trials. Now we could also set this to 1,000, and that's going to, if we restart this, it's going to consider 1,000 classes now. I'm using the double arrow there to run all 1,000. So notice that when we run this, the more trials that we run, our empirical probability under the data is going to get pretty close to the actual theoretical probability under the DIST column. So in this case, it's pretty close. We get 0.4 as opposed to 0.411. If we were to do this again for 10,000 or 100,000, it's going to get closer and closer to 0.411. That's called the law of large numbers. All right, so if you have any questions, let me know, but hopefully this explains it at least a little bit better.